let me define a term here, eustasy. It's kind of a complementary term to isostasy. Isostasy is up and down motion of the Earth's crust. Eustacy, spelled E-U-S-T-A-C-Y, okay? Vertical motion up and down of the ocean level.
Ah, okay.
Got it? So then if we talk about eustatic changes, we're talking about changes in ocean level. And the primary thing that, of course, affects changes in ocean level is the amount of glaciers on land. The more glaciers, the lower the ocean level. The fewer glaciers, the higher the ocean level. So there's when we talk about eustatic changes in ocean level, that's what we're talking about. Vertical motions of the Earth up and down, right? I mean, of the ocean up and down.
Right.
So this is what R.I. Walcott says. In a paper largely ignored in recent time, Daly, who wrote this in 1925, pointed out that changes in surface load over the oceans because of eustatic changes in sea level would deform the Earth. And according to Rhodesky's 1889 calculations of the surface deformation of a homogeneous elastic sphere, this deformation would be of significant magnitude. And anybody who's interested in the actual references here, I'm happy to provide that. Rhodesky goes back to 1889, and this was just simply calculations dealing with making assumptions about the elasticity of the Earth, and then what happens when you impress various loads upon it, when you remove those loads, when you move the loads around. Okay, so he's referred to two papers here that are establishing sort of the bedrock basis of these ideas of vertical motions of the Earth's crust. He goes on to say that in late glacial times, the major changes in load originated from the melting of ice over Fennoscandia and North America. Fennoscandia being northwestern Europe, and named basically after Scandinavia. And the simultaneous worldwide rise from the released water. Because the surface loads involve the lateral transfer of mass over the surface of the Earth, right? So must material be able to move laterally at depth within the asthenosphere. And this is that zone of plasticity below the crust that the crust is riding upon. It's the zone, it's the cushion between the crust and the upper mantle, the asthenosphere, okay? The already complex picture of relative movements of sea level is further complicated by the ground movements due to post-glacial rebound itself. The material that flows into the deglaciated area to produce uplift must come from somewhere. So we would expect a complementary depression outside the zone of uplift. If the whole mantle participated in the relaxation, these downward movements would be fairly widely spread over the Earth's surface, and therefore be of small and probably insignificant magnitude. But if, as we suppose here, the flow is restricted to a narrow asthenospheric shell, then the downwarp will occur in a restricted zone immediately peripheral to the uplift with large and significant displacements. Yeah. In Canada, the total amount of rebound at the center of uplift was between 400 and 1,000 meters.
Holy crap.
During the retreat of the ice sheet. Okay, so 1,000 meters, that's 3,280 feet.
Yeah, it's a kilometer, 1,000 meters.
It's a kilometer, 3,280 feet. Yeah, exactly. So that's pretty crazy.
Yeah, that's a lot of uplift.
That's pretty wild right there.
Yeah, so because I've always wondered, like there's the talk of the glacier melts, so that water is flowing off into the ocean basins. Now we have this rebound, so that the area where the glacier was sitting on is coming back up. So you have areas in the ocean that's going down, but all the water's flowing into the ocean basin as well, pushing it down more. So when they talk about a sea level rise of 400 feet, that isn't actually giving you a good idea of actually how much water moved in there, because the ocean is dropping as the water's pouring in, and it still goes up 400 feet. So how much did it actually add? Like, in other words, if it didn't drop, would it have gone up 1,000 feet? You see what I'm saying? In other words, if there wasn't that rebound, how much higher would that water have made the ocean levels actually?
Well, that would be relative, because what's happening here is we're seeing in this dynamic Earth model is that we've got these vertical changes happening all over the place. See, so this is a really, it comes back down to the geoid, which is going to be this kind of average distance, and everything is moving and compensating, but of course always there's lags, right? Delayed response times. The response times, it's not necessarily a smooth relaxation or a smooth adjustment. It can be jolty, and probably did involve a lot of seismic adjustment. In fact, there's evidence that yes, there was major heavy-duty seismic activity going on during the deglaciation process. Also volcanism.
Right. It makes sense. I mean, you got that much movement happening on the crust. There's going to be it has to make enormous adjustments across all faults, basically.
Well, and you throw in the fact that down the middle of the Atlantic is the Mid-Atlantic Rift.
Right.
You've got two plates there that are going like this.
Yes.
So okay. So then this is actually from 3 years earlier. This is R.K. Matthews, who was also a renowned marine geologist and oceanographer. He wrote this back in 1969. It was published in Earth and Planetary Science Letters, Volume 5, pages 459 through 462, if anybody is interested. R.K. Matthews was with the Department of Geological Sciences, Brown University at Providence, Rhode Island, for a little bit of background on him. And he was an important figure in the evolution of our understanding about the oceans. And this is what he wrote back in 1969. The title of the article: Tectonic Implications of Glacio-Eustatic Sea Level Fluctuations. So glacio-eustatic, okay, so there's Eustacy, and obviously all he's doing with this hyphenated term is connecting the glaciers with the eustatic changes in sea level. So he's saying glacio-eustatic, right? Just to make it clear that we're talking about changes in sea level resulting from changes in glacier mass.
Okay.
Right? Okay.
Right.
The possible tectonic implications of glacio-eustatic sea level fluctuations have received only minor attention in connection with such problems as ocean floor spreading. The purpose of this report is to point out that late Pleistocene sea level data suggest that the ocean basins have responded isostatically and by a significant amount to the loading and unloading of water associated with Pleistocene glaciation. Bloom, which is another reference which I can provide to somebody who really wants to get into this, summarizes data which indicate that continents and continental margins respond isostatically to variations in load of 10 bars or less, which is not much. If such small loads on continents and continental margins can bring about isostatic adjustment, might we expect whole ocean basins to respond isostatically to similar small loads? End of quote. And I think the answer that we could now say here all these decades later is yes. A half a century later, we can answer that question and say, yes, they can. They can do that.
Right, and so he's asking, like, even a small load, we should expect the ocean basins to change, and we're looking at an enormous load.
Yeah. Mm-hmm.
So we should expect huge shiftings of the ocean basins.
Yes, well, but not necessarily uniformly distributed over the ocean basins. That's another important idea. So, is there any actual evidence that there may have been a major isostatic adjustment of the Mid-Atlantic region that could be consistent with the narrative of a subsidence of an island group. Well, okay, so here is, now this isn't exactly, this is along, so what do we do? We'll look at a couple of studies here that have been made along the mid-Atlantic ridge. And this is from 1975, going back. Again, Earth and Planetary Science Letters. The title of the author is J. Honorez and others. The title of the article is Mesozoic Limestone from the Vima Offset Zone, Mid-Atlantic Ridge. So he's referring to an earlier report where the lead author, along with another oceanographer, reported on a dredging of shallow water limestone from the summit of a ridge within the offset zone of the Mid-Atlantic Ridge. The limestone was reported to contain detrital grains of quartz, orthoclase, and microcline. So what's the significance of that? Well, that indicates that a nearby source of granitic detritus was available during its deposition. Bonatti and Honorez have unsuccessfully attempted to explain their findings of granitic material and shallow water limestones on the basis of the present or recent geographical configuration of the equatorial Atlantic. So what that's saying is, what's interesting there is, granite is the rock that you find associated with continents. So what they're struggling with here is, why are they finding granite, detrital granite, along with shallow water limestones along the Mid-Atlantic Ridge? Why are they finding the remains of continents, in other words? So it goes on. Some of it gets kind of technical, and I'll try to skip over some of it just to not get it so technical here.
Is there an answer to? Do you have a speculative answer of how we got granite detritus in the limestone? Or you? Go,
yeah. I mean, obviously, it implies that there may be remnants of granitic crust or continental crust.
Okay, yeah, cool.
So Bonatti and Honorez suggest that the limestone and its granitic mineral grains must have been deposited sometime during the Mesozoic, which is, the great era of middle life, the Triassic, Jurassic, Cretaceous, that ended 66 million years ago with the extinction of the dinosaurs, right? Soon after the opening of the Atlantic Rift within a narrow and shallow proto-Atlantic basin. If Bonatti and Honorez's interpretation is correct, it would require that the crustal block capped by the limestone be left behind during the spreading of the Atlantic floor. This possibility would have important implications. So in other words, what he's suggesting there is that when the continents rifted and spread apart, there was a piece of continent left behind. You see, does that make sense?
Yes.
That a piece of a chunk of granitic continental type crust broke off, got disconnected from the. Now, was it part that became, Africa or Iberia, or was it part of North America? At this point, we don't know yet. But the idea now is that possibly there's a chunk of this granitic crust that has been left behind along the Mid-Atlantic Ridge.
When they first separated a long time ago, basically, is the idea.
Long time ago, yes.
Yeah.
Yes, right. So he goes on to talk about the existence of this high magnesium calcite, which indicates this recrystallization process. I guess I won't get into that because it gets pretty technical. But what happens is that they can look at the oxygen isotope ratios and tell, did the crystallization take place underwater or did it take place in the atmosphere? So one of the things that they were dredging up there, along with the shallow water limestones and the granitic grains, was this material that had this high magnesium calcite. Well, this particular type of high magnesium calcite forms in the atmosphere. So what he says, it's a clear indication of subaerial recrystallization. So subaerial, just like submarine, below the water, subaerial means below the air, but in the air, right?
Above the water.
Yes. The conclusions we derive from this study appear to confirm and extend the results previously by Bonatti and Honorez as follows. The components of the limestone constitute a homogeneous assemblage characteristic of a shallow water carbonate platform depositional environment. The crustal block capped by the limestone must have undergone large vertical movements, including episodes of immersion. Now, two words, immersion, immersion. Immersion, to be immersed in the water, but immersion means to come out of the water. So the word is spelled E-M-E-R-S-I-O-N, not I-M. See, immersion. So he's saying there that this included episodes of immersion. So get what he's talking about here. You got to get the picture in your mind without getting into all the technical details. Anybody who's listening who wants to, all that information is available. But the point is you've got a chunk of continental type crust left behind. It's capped by limestone, right? It has shown evidence of large vertical movements, including the fact that crystallization in the limestones is consistent with actually coming up out of the ocean into the air, subaerial. That's why he used that term. Yeah, if crustal spreading took place in this area, the block capped by the limestone apparently did not move with the spreading floor, but it has apparently undergone large-scale vertical movements. That's the takeaway from right. All of this.
And did they have any kind of a timeline on those vertical movements? I'm sure it's enormous.
No, they don't. In this, they make the point that there have been large vertical movements.
Right.
You know, that's the takeaway. We have to go to other sources to try to find more evidence of timing here. Here now, a follow-up article by E. Bonatti, B-O-N-A-T-T-I, if anybody wants to look him up, published a couple of years later in 1977. This is neogene crustal immersion and subsidence at the Romanche fracture zone, equatorial Atlantic. So at this point, their studies are near the equator, which puts them quite a bit south of where Plato's putative Atlantis would be, right? Okay. But the point is to establish the possibility, if not the plausibility, of large-scale vertical movements along the mid-Atlantic ridge. According to plate tectonics theory, the motions of the lithospheric plates, and the lithosphere is just the crust, right? The rock. Lithos means rock, so the sphere of rock is lithosphere, right? According to plate tectonic theory, the motions of lithospheric plates between an accretionary boundary or a spreading center and a consumptive boundary, which is subductive, a subduction zone, are essentially horizontal, taking place on the outer shell of the globe. However, some exceptions to this model appear to obtain in the vicinity of the major oceanic fracture zones, which would make sense because here's where the crust is the thinnest on the planet. You've got that, the spreading center is going to be, you could almost think of that as a hinge line, right? If you're going to get vertical movements due to isostatic adjustments, that would be the place, that would be the zones of least resistance. So the paper goes on to say, in this paper, we present an example of vertical tectonism of a transverse block located on the north side of the Romanche fracture zone. We demonstrate that the summit of this block was at or above sea level during the late Cenozoic. So the Cenozoic is the recent period of life. So late Cenozoic could mean anything from 10,000 years ago to a couple of 100,000 years ago. At this point, the time spread is too vast. But the point is that here is this evidence for this crustal block near the equators on the mid-Atlantic ridge that has undergone large-scale vertical movements up and down. And it demonstrates that this is possible, that this process is not some fantasy. It makes sense within the theory, the geophysical understanding of the way the Earth works. It's all consistent, and empirically, the evidence is beginning to accumulate.
Right, and that there's the I guess, the chemical or molecular evidence that there was subaerial formation of some of that stuff in that block, right? So that's clear, at least that in that sense, that it was above the water for some time at some point, which means there has to be enormous vertical movements of that.
Yes.
Part. Yeah,
yes. Like we're talking 1 to 2 miles.
Right. That's
We're talking 1 to 2 miles here. Let me go back. I'm going to do a screen share again. Take a good look at that. You see the mid-Atlantic ridge now?
Oh, yeah.
Going up. Look at this coming down, winding around like this. Now, we've got another huge fault line coming across here. So what you actually have here is a triple plate junction right here that trisects the Azores Plateau, which is this feature right here, which is a prominence. You see how it's uplifted from the rest of the floor around it? Right here.
Yeah, I see it.
Yeah.
That's pretty clear.
Yeah. So you not only have the mid-Atlantic ridge there, you've got this plate, you've got 2 plates here, this European plate and this African plate that meet this. You've actually got a triple junction there. So that would make that particular zone even more susceptible to isostatic movements due to eustatic changes in the Earth's crust. Now, notice the transverse faults. You see these vertical lines that run roughly perpendicular to the ridge?
Yep.
Okay. Now, I'm going to stop share and let's go back to what the boys were saying here. So Bonatti called attention to the significance of prominent east-west transverse ridges. These are what we were just looking at. Some shown already by Heesen and others, which run parallel to the equatorial Atlantic fracture zones. It has been suggested that such transverse morphology associated with fracture zones could not have been produced solely by crustal spreading from axial segments of the mid-Atlantic ridge, but that vertical tectonic motions exceeding, important word, exceeding those predicted by the simple plate tectonic model must have operated.
Mm-hmm. So those horizontal lines they're basically claiming that, or saying that there's evidence of those horizontal lines are evidence of enormous vertical movement.
Think of those lines as Earth's stretch marks.
Right. They can't be made by the plate tectonics model of it moving in a horizontal plane. Okay. Wow.
Yeah. So,
I'd seen those. I always thought that they were they were an artifact of the spreading, but these guys are saying that can't be right. It has to be vertical movements.
It's vertical movements.
They're fractures, right?
Yeah.
Yeah. So if you had that motion up and down, you can imagine it cracking on the edges.
Yeah. Yes, exactly. That's exactly what you can imagine, and that's exactly what you see there. Let's go on with one more to conclude this report from 1977. Partly phosphatized oolitic biogenic limestones. Get that?
Oolitic. Got it.
You got it. Okay.
Phosphatized oolitic. Yeah.
Oolitic. Well, it's not important. Anybody can look this up, but here's what's important about that particular kind of limestones. They were recovered from 950 to 1,300 meters below sea level. And 1,300 meters would be 4,264 feet. Were recovered from 2 sites near the crest of a transverse ridge. Some of the biogenic constituents of the limestones, their paleofacies assemblage, and the presence of well-developed oolitic facies indicate that, and here's the important part, the limestones formed in very shallow water close to sea level. In addition, several features of this limestone suggest that the summit of the transverse ridge might have undergone episodes of immersion. In other words, it may have come up so much that it actually came above the surface of the ocean. And now it's found 4,264 feet below.